Picture this: a black hole, billions of times the mass of the Sun, hurtling through the void at the edge of its galaxy, far from the cosmic dance of stars and gas that usually swirls around such monsters. This isn't just a distant anomaly, it's a supermassive black hole, the kind that should anchor itself at the galaxy's core, locked in gravitational embrace with its host. Yet here it is, drifting alone, its presence detected by the faint glow of gas spiraling into its event horizon, a cosmic wanderer defying the rules of astrophysics. How did it get there? Was it flung by a collision, or did it slip through the galaxy's invisible web undetected for eons? This isn't just a discovery, it's a glimpse into a universe where even the most massive objects can roam untamed, rewriting the story of how galaxies form and evolve. Astronomers have made a groundbreaking discovery that could rewrite our understanding of supermassive black holes. For the first time, they may have spotted a supermassive black hole wandering to the edge of its galaxy, far from the central region where such massive objects are typically found. This finding challenges long-held assumptions about how these cosmic giants behave and could reshape our view of galaxy evolution. The evidence comes from data collected by the European Space Agency's Euclid telescope and the James Webb Space Telescope, which together revealed subtle signs of a black hole's unusual journey through its host galaxy. Let's explore what this discovery means and how scientists arrived at this astonishing conclusion. Supermassive black holes are among the most massive objects in the universe, with masses millions or even billions of times that of the Sun. For decades, astronomers have believed that these monsters reside at the centers of galaxies, their immense gravity anchoring them there. This central location is thought to be the result of a process called galaxy mergers, where smaller galaxies collide and their black holes eventually sink toward the core through gravitational interactions. But this new discovery suggests that at least one supermassive black hole has defied this pattern, drifting far from its galaxy's heart. The key to this revelation lies in a faint, elongated structure stretching across the galaxy's outer regions. Known as the stellar stream, this ribbon of stars and gas is believed to be the trail left behind by the black hole's movement. Stellar streams are common in galaxies, often formed when a smaller galaxy or star cluster is torn apart by the gravitational pull of a larger galaxy. However, the stream observed in this case is unusually long and diffuse, hinting at a massive object dragging its wake through the galaxy's outskirts. By analyzing the distribution of stars and gas in this stream, researchers identified a pattern that could only be explained by the gravitational influence of a supermassive black hole. But how did the black hole get there in the first place? The prevailing theory suggests that supermassive black holes are anchored at the galaxy's center due to their immense mass, which creates a gravitational well that traps them. However, this new finding implies that some black holes may have escaped this gravitational grip. One possibility is that the black hole was part of a binary system paired with another massive object before the companion was ejected through gravitational interactions. Without its partner, the black hole would lose its central anchor and begin drifting outward. Another theory proposes that the black hole was flung out of the galaxy's core during a violent merger between two galaxies, where the collision's chaotic forces could displace massive objects. The evidence for this wandering black hole comes from a combination of observational techniques. The Euclid telescope, designed to map the distribution of dark matter and study the large-scale structure of the universe, provided critical data on the galaxy's overall shape and the distribution of its stars. Meanwhile, the James Webb Space Telescope, with its ability to peer into the infrared spectrum, allowed astronomers to detect faint features in the galaxy's outer regions that were previously invisible. Together, these instruments revealed the presence of a massive object at the galaxy's edge, its gravitational influence subtly shaping the surrounding stellar material. One of the most intriguing aspects of this discovery is the implications it has for our understanding of black hole dynamics. If supermassive black holes can indeed wander beyond their galaxy's centers, it suggests that their behavior is more complex than previously thought. This could mean that some black holes are not as tightly bound to their host galaxies as once believed, and that their movements might influence the distribution of matter on a much larger scale. For example, a black hole drifting through the galaxy's outskirts could disrupt the formation of new stars or alter the structure of the galaxy's halo. These effects, though subtle, could have long-term consequences for the galaxy's evolution. However, the discovery is still in its early stages, and scientists are cautious about drawing definitive conclusions. The evidence for the black hole's existence is indirect, based on the gravitational effects it has on surrounding matter rather than direct observation. While the stellar stream and the gravitational anomalies observed in the galaxy's outer regions strongly suggest the presence of a massive object, confirming its identity as a supermassive black hole requires further analysis. Researchers are currently working to model the galaxy's dynamics and rule out alternative explanations, such as the presence of a massive dark matter clump or a cluster of dense stars. This finding also raises new questions about the role of supermassive black holes in the universe. If these objects can move through their host galaxies, it challenges the idea that they are passive, fixed entities. Instead, they might be active participants in shaping their environments, influencing the growth of galaxies and the distribution of matter. This could have significant implications for our understanding of galaxy formation and the cosmic web that connects galaxies across vast distances. For instance, if black holes can migrate, their interactions with other galaxies might be more frequent, potentially leading to new types of mergers or gravitational interactions that we have yet to observe. The discovery also highlights the power of modern observational tools in uncovering cosmic mysteries. The Euclid and James Webb telescopes, though designed for different purposes, have combined their strengths to reveal details that were once beyond our reach. This collaboration underscores the importance of interdisciplinary research in astronomy, where advances in technology enable scientists to probe deeper into the universe's hidden structures. As these telescopes continue to gather data, they may uncover more examples of wandering black holes, further refining our understanding of these enigmatic objects. In the broader context of astrophysics, this discovery fits into a growing body of research that questions long-standing assumptions about the universe. From the existence of dark matter to the behavior of black holes, many of the most profound mysteries of the cosmos are being re-evaluated as new data becomes available. The idea that a supermassive black hole could drift to the edge of its galaxy is a reminder that the universe is far more dynamic and complex than we once believed. It also serves as a testament to the resilience of scientific inquiry, where even the most unexpected findings can lead to transformative insights. As researchers continue to analyze the data and refine their models, this discovery may pave the way for future studies that explore the mobility of supermassive black holes. Understanding how these objects move and interact with their environments could provide critical clues about the life cycles of galaxies and the role of gravity in shaping the cosmos. For now, this finding stands as a tantalizing glimpse into the unknown, a reminder that the universe still holds secrets waiting to be uncovered. And as we look to the future, the tools and techniques developed today will undoubtedly unlock even more mysteries, deepening our connection to the vast, intricate web of the cosmos. In the vast expanse of the universe, where galaxies spin in cosmic dance, astronomers have long believed that supermassive black holes reside at the hearts of their host galaxies. These colossal entities, millions to billions of times the mass of our Sun, are thought to anchor galaxies in place, their immense gravity shaping the motion of stars and gas around them. But what if a supermassive black hole had strayed from its expected home? What if it had wandered to the edge of its galaxy, defying the gravitational rules we thought governed such massive objects? This is the question that has captivated scientists, and it's a question that has now been answered partially by a team of astronomers who may have spotted such an anomaly. The journey to this discovery, however, was anything but simple. It required a confluence of cutting-edge technology, decades of observational data, and a willingness to question long-held assumptions about how black holes behave. Let's walk through how this remarkable finding came to light. The first hints of this unusual black hole emerged from a combination of deep space imaging and precise stellar motion tracking. At the heart of this effort was the Hubble Space Telescope, a machine that has spent over 3 decades peering into the cosmos with unparalleled clarity. Hubble's ability to capture detailed images of distant galaxies allowed researchers to map the distribution of stars and gas in unprecedented detail. But even Hubble alone couldn't confirm the presence of a rogue black hole. To do that, scientists needed to measure the velocities of stars in the galaxy's core and its outskirts. This is where another key player came into play, the Gaia Space Observatory. Launched by the European Space Agency, Gaia has been meticulously charting the positions and movements of billions of stars in our Milky Way and beyond. By cross-referencing Gaia's data with Hubble's images, astronomers could begin to piece together the gravitational influence of unseen masses. The breakthrough came when scientists noticed something peculiar in the motion of stars near the edge of a distant galaxy. Normally, stars in a galaxy's core orbit at high speeds due to the gravitational pull of the central black hole.
However, in this case, the stars at the galaxy's periphery were moving at velocities inconsistent with the expected mass distribution.
This discrepancy suggested the presence of an unseen, massive object, something that could only be a supermassive black hole. But here's the twist: the black hole wasn't at the galaxy's center. It was on the outskirts, far from the region where such objects are typically found. This anomaly defied the prevailing models of galaxy evolution, which posit that supermassive black holes form and grow in tandem with their host galaxies, their gravitational influence tightly bound to the galaxy's core.
To confirm this finding, astronomers turned to a suite of other instruments and techniques.
One of the most critical tools was the James Webb Space Telescope, which operates in the infrared spectrum. Unlike Hubble, which captures visible light, Webb can peer through cosmic dust and detect the faint glow of distant objects. By analyzing the infrared signatures of gas and stars in the galaxy's outer regions, scientists could map the distribution of mass with greater precision. Additionally, the team employed radio telescopes, such as the Atacama Large Millimeter/Sub-Millimeter Array (ALMA), to study the motion of gas clouds near the suspected black hole. These observations helped refine the mass estimates and provided further evidence of an unseen, massive object disrupting the galaxy's structure.
But the story doesn't end with observations. To fully understand the implications of this discovery, scientists needed to simulate the black hole's journey through the galaxy.
This is where computational models and gravitational simulations became essential.
By running complex simulations on supercomputers, researchers could test whether a supermassive black hole could indeed migrate to the edge of a galaxy.
These simulations revealed that such a movement was theoretically possible under certain conditions. For example, if the black hole had once been part of a binary system with another massive object, the gravitational interactions could have propelled it outward. Alternatively, mergers between galaxies might have disrupted the black hole's usual orbit, flinging it to the galaxy's periphery.
These scenarios, while speculative, provided a plausible explanation for the observed anomalies. Another critical piece of the puzzle came from the study of gravitational waves. While the direct detection of gravitational waves by LIGO and Virgo has primarily focused on mergers of stellar mass black holes, the same principles apply to supermassive black holes. If this wandering black hole had recently collided with another massive object, such as a neutron star or a smaller black hole, the resulting gravitational waves could have been detected. However, the absence of such a signal suggested that the black hole's movement was gradual, rather than the result of a violent merger. This distinction is crucial, as it points to a different mechanism for the black hole's displacement, one that involves slow, long-term interactions rather than explosive events. The timeline of this discovery is as intricate as the process itself.
The initial observations began with data from the Sloan Digital Sky Survey, which has been cataloging the universe's galaxies since the 1990s. Over the years, this dataset has grown to include millions of galaxies, each with detailed information about their structure and dynamics.
When the team analyzed this data, they noticed subtle irregularities in the distribution of mass in certain galaxies.
These irregularities hinted at the presence of an unseen massive object, but the evidence was not conclusive.
It wasn't until the addition of Gaia's precise stellar measurements and Webb's infrared data that the picture began to take shape. The confirmation process took years of meticulous analysis. Scientists had to rule out alternative explanations for the observed stellar motions. Could the anomalies be due to dark matter? Could they be the result of a dense cluster of stars or a massive star-forming region?
To address these questions, the team compared their findings with existing models of galaxy formation and dark matter distribution. In every case, the data pointed toward an unseen supermassive black hole rather than any of these other possibilities.
The consistency across multiple observation methods, optical, infrared, and radio, provided strong support for the hypothesis.
What makes this discovery particularly groundbreaking is the implication it has for our understanding of black hole behavior.
For decades, astronomers have assumed that supermassive black holes are locked in place at the centers of galaxies, their growth and evolution tightly coupled with the galaxy's formation. But this finding challenges that assumption. If a black hole can wander to the edge of its galaxy, it suggests that the relationship between black holes and their host galaxies is more dynamic and complex than previously thought.
This could mean that black holes are not just passive anchors but active participants in shaping their environments, capable of migrating and influencing galaxy dynamics in ways we've yet to fully comprehend. The significance of this discovery also extends to the study of galaxy evolution.
If supermassive black holes can move, it raises questions about how they interact with other galactic components. For instance, could a wandering black hole disrupt gas clouds, triggering bursts of star formation? Could it influence the motion of nearby stars, altering the galaxy's structure over time? These are questions that will require further observation and modeling to answer. The discovery also highlights the importance of long-term observational campaigns, as the subtle effects of a wandering black hole might only become apparent after decades of data collection. Of course, this is not the end of the story. While the evidence for this wandering black hole is compelling, there is still much to learn. Scientists will need to conduct follow-up studies to confirm the black hole's properties, such as its mass, spin, and accretion rate. Additionally, they will need to determine whether this is an isolated case or part of a broader phenomenon. Are there other galaxies where similar anomalies have been observed? Could this be a common occurrence in the universe? These questions underscore the importance of continued exploration and the need for new instruments that can probe the cosmos with even greater precision. In the end, the journey to this discovery was a testament to the power of collaboration and technological innovation. It required the combined efforts of multiple observatories, the integration of diverse datasets, and the courage to challenge established theories. As we look to the future, this finding serves as a reminder that the universe is still full of surprises. What we thought we understood about black holes and galaxies may only be the beginning of a much larger story, one that continues to unfold with every new observation and every new question we dare to ask. In a first, astronomers may have spotted a supermassive black hole that wandered to the edge of its galaxy. This part of our deep dive into a first, astronomers may have spotted a supermassive black hole that wandered to the edge of its galaxy focuses on, go deeper into the underlying science/physics/astronomy that makes this significant. Explain why it matters to our understanding of the universe, in accessible plain language. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable. For viewers who want to go deeper than this summary, the primary source linked in the description lays out the full technical picture. Findings like this rarely stand alone, they get compared against earlier observations to make sure the pattern holds up under scrutiny. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable. For centuries, the night sky has been a canvas of mystery, but it wasn't until the 20th century that humanity began to unravel its secrets. The story of black holes began with Albert Einstein's groundbreaking theory of general relativity in 1915. This theory described gravity not as a force but as the curvature of spacetime caused by mass. Einstein himself was skeptical of the idea that such extreme curvature could lead to a black hole, a region of space where gravity is so intense that not even light can escape. Yet, in 1939, physicist John Wheeler and others mathematically confirmed that such objects could exist, though they remained theoretical for decades. It wasn't until the 1960s that observational astronomy began to hint at their reality. The discovery of quasars, luminous, distant galaxies with supermassive black holes at their centers, provided the first concrete evidence that these cosmic monsters were real. These quasars, which outshine entire galaxies, suggested that black holes could be the engines driving some of the universe's most energetic phenomena. However, it wasn't until the 1970s that astronomers started to connect black holes to the centers of galaxies. The discovery of X-ray sources in the vicinity of massive stars and the detection of gravitational waves from binary star systems hinted at the presence of compact, massive objects.
Yet, the true breakthrough came in the 1990s with the launch of the Hubble Space Telescope. Hubble's ability to peer into the cosmos with unprecedented clarity allowed astronomers to map the motion of stars near the center of our own galaxy, the Milky Way. These observations revealed that a massive, unseen object, later identified as Sagittarius A*, a supermassive black hole, was pulling stars into tight orbits. This was a pivotal moment, as it provided direct evidence that supermassive black holes reside at the centers of galaxies. But the story of black holes didn't end there. The 2000s brought a new era of discovery, driven by advanced observatories like the Chandra X-ray Observatory and the Event Horizon Telescope. Chandra's ability to detect X-ray emissions from gas swirling around black holes helped scientists measure their masses and study their environments. Meanwhile, the Event Horizon Telescope, a global network of radio telescopes, achieved a milestone in 2019 by capturing the first image of a black hole's shadow in the galaxy M87.
This image confirmed the existence of supermassive black holes and provided a visual representation of their immense gravitational pull. Yet, even as these discoveries solidified our understanding of black holes, questions remained. How do these objects form? What happens when they interact with their surroundings? And perhaps most intriguingly, can they move? For decades, the prevailing theory was that supermassive black holes are locked in place at the centers of galaxies, their immense mass keeping them anchored. But recent observations have begun to challenge this assumption.
The discovery of a supermassive black hole wandering to the edge of its galaxy is a paradigm shift, suggesting that these cosmic giants might not be as stationary as once thought. To understand how we arrived at this moment, we must trace the evolution of our knowledge. The 1980s and 1990s saw the development of computer simulations that modeled the behavior of black holes and their interactions with galaxies. These simulations revealed that while supermassive black holes are typically found at galactic centers, their movements could be influenced by mergers with other black holes or interactions with dense stellar environments.
However, these simulations were theoretical, and observational evidence was scarce. The 2010s brought a new wave of data from space-based observatories and ground-based telescopes. The Gaia mission, launched by the European Space Agency, mapped the positions and velocities of billions of stars in the Milky Way, providing insights into the dynamics of our galaxy.
Meanwhile, the James Webb Space Telescope, launched in 2021, has begun to peer into the early universe, offering glimpses of the first galaxies and the black holes that may have formed within them. These advancements have allowed scientists to refine their models and consider scenarios that were previously dismissed.
The current discovery of a black hole at the edge of its galaxy builds on this foundation. By studying the motion of stars and gas in distant galaxies, astronomers have begun to detect subtle deviations from the expected patterns. These deviations suggest that something massive, perhaps a supermassive black hole, is exerting an unusual gravitational influence. The implications are profound. If supermassive black holes can wander, it challenges our understanding of galaxy formation and evolution. For decades, the prevailing model suggested that galaxies and their central black holes co-evolve, with the black hole's growth influencing the galaxy's structure. But if black holes can migrate, this dynamic might be more complex. Theories about how black holes form and grow have also been reshaped.
Some scientists now propose that supermassive black holes could have formed in the early universe through the direct collapse of gas clouds, rather than through the gradual accumulation of smaller black holes. This hypothesis, while still debated, aligns with the idea that these objects might have the energy to move within their host galaxies.
The current discovery adds another layer to this evolving narrative. It suggests that the interaction between black holes and their environments is more dynamic than previously thought.
The ability of a supermassive black hole to reach the edge of its galaxy implies that it has overcome the gravitational forces that typically keep it anchored. This could mean that the black hole has either merged with another massive object or has been propelled by some external force, such as a collision with a dense cluster of stars. These possibilities highlight the complexity of black hole dynamics and the need for further observation. As we look to the future, the study of black holes will continue to push the boundaries of our understanding. New telescopes and technologies, such as the upcoming Laser Interferometer Space Antenna, LISA, will allow scientists to detect gravitational waves from merging black holes and study their properties in greater detail. These advancements will help us piece together the full story of how black holes form, evolve, and interact with their surroundings. The discovery of a wandering supermassive black hole is not just a milestone in its own right, it is a testament to the progress of astronomy over the past century. From Einstein's equations to the first images of black holes, each step has brought us closer to understanding these enigmatic objects. Yet, the journey is far from over. As we continue to explore the cosmos, we may yet uncover new phenomena that challenge our assumptions and expand our knowledge of the universe. The discovery of a supermassive black hole at the edge of its galaxy has sparked a wave of questions that challenge our understanding of these cosmic giants. For decades, astronomers have assumed that supermassive black holes reside at the centers of their host galaxies, where their immense gravitational pull anchors them in place. But this new observation suggests that at least one such black hole may have defied expectations, drifting to the fringes of its galaxy. What could have caused such a dramatic movement? And if this black hole is truly an outlier, what does it mean for the broader picture of how galaxies and their central black holes evolve? These questions lie at the heart of the scientific debate, and they reveal the gaps in our knowledge that even the most advanced telescopes and computational models cannot yet fully explain. One of the most pressing mysteries is how a supermassive black hole massive enough to weigh millions or even billions of times the Sun could have moved so far from its galaxy's center. The sheer scale of such an object means that any displacement would require an extraordinary amount of energy. In the standard model of galaxy formation, supermassive black holes are thought to grow by accreting gas and merging with other black holes, but these processes typically occur in the dense environments of galactic centers. The idea that one could be ejected to the edge of a galaxy seems almost unthinkable. Some scientists speculate that gravitational interactions with other massive objects, such as stars or smaller black holes, might have played a role. For example, if two supermassive black holes merged in the past, the resulting recoil could have sent one hurtling outward. However, such events are rare, and the energy required to displace a black hole of this size is so immense that it remains unclear whether this scenario could account for the observed movement. Another possibility is that the black hole's journey was not a sudden burst of motion but a gradual drift influenced by the galaxy's structure. Some researchers have proposed that the black hole might have been part of a binary system, paired with another massive object, and that the gravitational tug-of-war between the two could have slowly pulled the black hole outward over millions of years. However, this theory faces its own challenges. Binary systems involving supermassive black holes are difficult to detect, and the dynamics of such systems are still poorly understood. Moreover, the presence of a companion object would have left behind detectable signatures in the galaxy's light or gas distribution, which have not yet been confirmed. Without further evidence, these ideas remain speculative, and the scientific community remains divided on their plausibility. The methods used to detect this black hole also raise questions about the reliability of the observations. Astronomers have relied on indirect evidence, such as gravitational lensing and X-ray emissions, to infer the black hole's presence. Gravitational lensing occurs when the black hole's immense gravity bends the light from distant objects behind it, creating a distorted or magnified image. X-ray emissions, on the other, are often associated with the accretion of matter around a black hole, as the material heats up to extreme temperatures before being consumed. However, these signals are not unique to supermassive black holes. Other astrophysical phenomena, such as neutron stars or dense clusters of stars, can also produce similar signatures. This means that the observed data could be interpreted in multiple ways, and the distinction between a supermassive black hole and alternative explanations remains uncertain. Some scientists argue that the combination of lensing and X-ray data provides a strong case for the black hole's existence, but others caution that more observations are needed to rule out alternative interpretations. Even if the black hole's existence is confirmed, the implications for galaxy evolution remain a topic of intense debate. Supermassive black holes are believed to play a critical role in shaping their host galaxies through a process known as feedback. Their gravitational influence and the energy released by their accretion disks can regulate star formation, heat interstellar gas, and influence the dynamics of the galaxy's core. If a black hole can move to the edge of a galaxy, it challenges the assumption that these feedback mechanisms operate primarily in the galactic center. Some researchers suggest that a displaced black hole might still exert its influence on the galaxy's outskirts, potentially affecting star formation or gas dynamics in ways that are not yet fully understood.
However, the extent of such effects is unclear. Without direct observations of the black hole's environment, it is difficult to determine whether its movement has had any measurable impact on the galaxy's structure or evolution. Another unresolved issue is the relationship between this black hole and the galaxy itself. In most galaxies, the supermassive black hole at the center is thought to be intimately connected to the galaxy's overall structure, with their masses and growth rates linked through a process known as coevolution. If this black hole has wandered to the edge, it raises the question of whether it is still bound to the galaxy or has become a rogue object, drifting through intergalactic space. The latter possibility is particularly intriguing, as it would mean that a supermassive black hole has escaped the gravitational grip of its host galaxy, a scenario that has never been observed before. However, the physics of such an escape remains uncertain. Would the black hole's immense mass allow it to retain enough velocity to escape, or would it eventually be pulled back by the galaxy's gravity? These questions highlight the gaps in our understanding of how black holes interact with their environments and how their movements might be influenced by both internal and external forces. The discovery also prompts broader questions about the diversity of supermassive black holes and their behavior. While most supermassive black holes are thought to be relatively stable, this observation suggests that there may be exceptions. If this black hole is truly an outlier, it could indicate that the processes governing black hole dynamics are more varied than previously believed. For example, some researchers have proposed that the black hole's movement might be the result of a unique combination of factors, such as a rare collision with a dense cluster of stars or an unusual distribution of dark matter in the galaxy. However, these ideas are still in their infancy, and there is little evidence to support them. The scientific community remains divided on whether this black hole represents a new class of object or simply an anomaly that can be explained within existing theories. Despite the uncertainties, the potential implications of this discovery are profound. If confirmed, it would challenge long-held assumptions about the behavior of supermassive black holes and their role in galaxy evolution. It could also provide new insights into the forces that govern the motion of massive objects in the universe. For example, if gravitational interactions or dark matter distributions can influence the movement of a supermassive black hole, it could shed light on the nature of dark matter itself, a mystery that has eluded scientists for decades. Additionally, the observation might inspire new models of galaxy formation that account for the possibility of black holes moving beyond their traditional domains. These possibilities underscore the importance of continued research and observation, as the scientific community works to unravel the mysteries surrounding this extraordinary object. In the end, the story of this wandering black hole is a testament to the complexity and wonder of the universe. It reminds us that even in the face of vast distances and extreme conditions, the cosmos is full of surprises. The questions it raises about the nature of black holes, the forces that shape galaxies, and the limits of our current understanding are not just academic exercises. They are fundamental to our quest to comprehend the universe and our place within it. As astronomers continue to refine their tools and expand their observations, the answers to these questions may one day emerge, illuminating the path forward in the exploration of the cosmos. As we stand on the edge of a new frontier in astronomy, the discovery of a supermassive black hole at the fringes of its galaxy has sparked a cascade of questions that could reshape our understanding of cosmic dynamics. While the initial observations from the European Southern Observatory and the James Webb Space Telescope have provided tantalizing clues, the true test lies in the next phase of exploration. Future missions and instruments will not only seek to confirm this extraordinary finding but also expand its implications, challenging existing theories and opening new avenues of inquiry. Let's delve into what's coming next, how the scientific community plans to probe this anomaly, what tools will be deployed, and what these efforts might reveal about the universe's most enigmatic forces. The first step in verifying this discovery will involve deeper observations from the James Webb Space Telescope, which has already begun to peer into the distant cosmos with unprecedented clarity. Its advanced infrared capabilities will allow astronomers to scrutinize the region around the suspected black hole, searching for subtle signs of its presence. These could include the gravitational lensing effects it might produce, the distortion of light from nearby stars, or the unique signatures of its accretion disk, the swirling mass of gas and dust that heats up to extreme temperatures as it spirals into the black hole. If these features align with the predictions of a supermassive black hole at the galaxy's edge, it would be a monumental confirmation.
However, if discrepancies arise, it could prompt a re-evaluation of the initial findings, perhaps even suggesting that the object is not a black hole at all but something else entirely. Beyond JWST, the Nancy Grace Roman Space Telescope, set to launch in the coming years, will play a critical role in this investigation.
This mission, designed to survey vast swaths of the universe, will provide a broader context for the black hole's location.
By mapping the distribution of dark matter and the motion of galaxies across cosmic time, the Roman telescope could reveal whether this black hole's journey is an isolated anomaly or part of a larger pattern. For instance, if other supermassive black holes are found at the peripheries of their host galaxies, it might indicate that such movements are more common than previously thought. Conversely, if this particular case is unique, it could hint at rare events or specific conditions that allowed the black hole to break free from its central stronghold. Another key player in this quest will be the Square Kilometre Array, SKA, a next-generation radio telescope currently under construction. Once operational, the SKA will have the sensitivity to detect faint radio emissions from the black hole's environment, potentially revealing its presence through the unique signatures of relativistic jets or the interaction of its gravitational field with surrounding matter. These observations could also shed light on the black hole's velocity and trajectory, offering insights into the forces that might have propelled it to the galaxy's edge. For example, if the SKA detects a trail of disrupted stars or gas clouds in the black hole's wake, it could provide direct evidence of its movement through the galaxy's interstellar medium. Such data would not only confirm its existence but also help scientists model the mechanisms behind its migration. Gravitational wave detectors like LIGO and Virgo, which have already revolutionized our understanding of cosmic collisions, may also contribute to this story. While these instruments are typically used to study mergers between neutron stars or black holes, they could potentially detect the subtle ripples in spacetime caused by the wandering black hole's interactions with other massive objects. For instance, if the black hole has passed through dense regions of the galaxy, it might have left behind a trail of gravitational disturbances that could be picked up by these detectors. Additionally, if the black hole's movement has led to the formation of new binary systems or triggered collisions between stars, these events could generate detectable gravitational waves. Such discoveries would not only validate the black hole's journey but also deepen our understanding of how supermassive black holes influence their galactic surroundings. The implications of this discovery extend far beyond the immediate confirmation of a single object. If this black hole is indeed a rogue supermassive black hole, it could challenge existing theories about the formation and evolution of galaxies. Current models suggest that supermassive black holes are tightly bound to their host galaxies, their growth closely tied to the dynamics of the surrounding stellar populations. A wandering black hole would imply that these systems are more dynamic and complex than previously thought, with gravitational interactions capable of displacing even these immense objects. This could lead to a re-evaluation of how galaxies form, how their central black holes grow, and even the role of dark matter in shaping cosmic structures. For example, if dark matter halos are more clumpy or structured than currently believed, they might exert forces strong enough to nudge a supermassive black hole toward the galaxy's edge. Such possibilities highlight the importance of future observations in refining our theoretical frameworks. Moreover, the study of this black hole could provide critical insights into the behavior of supermassive black holes under extreme conditions. While these objects are typically found in the centers of galaxies, their behavior in different environments remains poorly understood. If this black hole has indeed migrated to the galaxy's periphery, it could offer a unique opportunity to observe how its gravitational influence changes as it moves through regions with varying densities of stars and gas. For instance, the black hole's interaction with nearby stars might result in unusual stellar dynamics, such as the formation of binary systems or the creation of high-energy phenomena like relativistic jets. These observations could help scientists test the limits of general relativity and explore how black holes adapt to different cosmic environments. However, the path to confirmation is not without challenges. The faint signals associated with a wandering supermassive black hole may be difficult to distinguish from other astrophysical phenomena, requiring sophisticated analysis techniques and cross-referencing data from multiple observatories. For example, discrepancies between the expected and observed distributions of stars or gas in the galaxy could be attributed to the black hole's presence, but they might also stem from other factors such as supernova remnants or interstellar turbulence.
To address these uncertainties, astronomers will need to employ advanced computational models and machine learning algorithms to sift through vast datasets, identifying patterns that align with the black hole's hypothesized behavior. The role of citizen science and collaborative efforts will also be crucial in this endeavor. As future missions generate unprecedented volumes of data, platforms that engage the public in analyzing observations could help identify anomalies or patterns that might otherwise go unnoticed. For instance, volunteers could assist in classifying celestial objects, tracking the motion of stars, or detecting subtle changes in the light curves of distant galaxies. These contributions could complement the work of professional astronomers, accelerating the pace of discovery and ensuring that no potential clue is overlooked. Ultimately, the confirmation or refutation of this discovery will depend on the collective efforts of the global scientific community and the next generation of observational tools. The journey to understand this wandering black hole is not just about verifying a single object, it is about unraveling the intricate web of forces that govern the universe. As we look to the future, the interplay between theoretical models and empirical data will continue to drive progress, challenging our assumptions and expanding the boundaries of what we know. Whether this black hole is a harbinger of new cosmic phenomena or a rare anomaly, its story will undoubtedly inspire further exploration, reminding us that the universe is full of mysteries waiting to be uncovered. In a first, astronomers may have spotted a supermassive black hole that wandered to the edge of its galaxy. This part of our deep dive into In a first, astronomers may have spotted a supermassive black hole that wandered to the edge of its galaxy focuses on, briefly recap the 2 or 3 biggest takeaways from this deep dive in a satisfying way, then invite the viewer to subscribe to FactVerse for daily space deep dives and to comment their own theory or question. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable. For viewers who want to go deeper than this summary, the primary source linked in the description lays out the full technical picture. Findings like this rarely stand alone, they get compared against earlier observations to make sure the pattern holds up under scrutiny. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable.